Hello everyone, and welcome to my presentation about DirectPro, a long fiber direct injection molding process, provided to you by Yizumi, industry's best cost-effective solution provider with leading technologies. During the next approximately 30 minutes, I will talk with you about fiber reinforced plastics in common. Then I will introduce our DirectPro approach for long glass fiber direct injection molding to you, explain something about the properties of long glass fiber reinforced parts, and will introduce you some current activities that we have with our customers and partners for DirectPro. So part 1, fiber reinforced plastics. Usually fiber reinforced plastics consist of at least 3 different portions. First one is fibers, which can be inorganic, organic, natural or even metallic fibers, a matrix polymer, which could be from thermoplastics, elastomers or even thermosets, 2 additives, which might be necessary to increase the bonding between the fibers and the matrix polymer, or to even get us some other interesting properties like colorants, fillers or anything else. These 3 together bring us to the fiber reinforced plastics we're using today. Due to the different portions and setups, we can have tailor-made properties for mechanical, dynamical, or thermal properties. We find new possibilities and substitutions for former metallic parts, and can also use these fiber reinforced plastics for lightweight design, increasing energy efficiency or even economic efficiency. Usually there are 3 different types of fiberglass reinforced plastics. First one would be short fiber pellets, which are made out of fiber, matrix polymer and additives, which can be compounded, then pultruded and will be in some kind infiltrated. These are typically used for injection molding machines or for extrusion processes and have fiber lengths between 0.4 to 0.8 millimeters. On the other hand, there are so-called long fiber pellets, which are usually pultruded from continuous fibers, are then cut to lengths of 8 up to 25 millimeters and are then used as granules and pellets for injection molding or extrusion machines. And the last one, these are semi-finished products, which could be, for example, GMTs or organic sheets or organic metal sheets, like you know them, called endless fiber fabrics, which are used for example, compression molding or even injection molding. And all these 3 types are typically used for direct processing approach. On the left side here we have a look about the common mechanical properties of plastic types which correspond to the overall length of the fibers introduced. Here on the left side you can see the diagram where the length of the fiber is dependent on the mechanical properties. And you can see coming from a length from 0.1 to 1 millimeter, there's a threshold when where the mechanical properties dramatically increase up to a length of 10 millimeter, and beyond 10 millimeter we won't see any more mechanical increase at all or in total. Of course, it's not just about the length of the fibers, but there's also other things which influence the overall mechanical properties. For example, the used fiber type, for example, if you're using a glass fiber or a carbon fiber, the used matrix material, if you're using PP or nylon or PC-ABS, the fiber length distribution, of course, so the overall length distribution and deviation from very short to very long fibers, fiber orientations inside our part, the diameters of the fibers, and other stuff like the adhesion between fiber and matrix, the used additives, and even the temperature when the parts are used. So, like I mentioned before, these parts usually consist of fiber, matrix, polymer, and additives. And to be honest, these for the pre-processing to make these parts, this is also always a matter of money. So normally these granules cost multiple times the money that you have to use for unfilled materials, although they bring you better mechanical properties, it will cost much more. So there should be a possibility to decrease that overall invest, especially when you're going inside very big parts or continuously produced parts. You will not only have a high capital investment, but also high running costs due to the high material costs for these granules and pellets. So there should be a possibility to decrease this money for the material costs. So from our point of view, there are two objectives to keep in mind. First one is the objective about the injection molding, which means we should have a modified, ideally a modified standard injection molding machine with a simple setup with overall low system costs, which could be highly scalable, up from low small clamping forces up to very high clamping forces. Should also be upgradable, so it's not only possible to use it for a special type of injection molding machine, but ideally for any type of machine: hydraulics, hybrids, fully electric, 2-platen, 3-platen, toggle lever, hydraulics, and so on and so on. The programming and the monitoring should also be easy and should be implemented into the machine control system without any further control system. And of course, the machine should still be usable for standard injection molding tasks if you do not want to use it only for special processes. On the other hand, you have the fibers objective, of course. As I mentioned, the mechanical properties are highly influenced by the overall fiber lengths, so it should be possible to define initial lengths or different lengths for which should be eventually at the end of the process in your parts. It should be possible to have nearly any fiber content you recommend or you wish. It should be possible to change the content of the fibers inside our parts during the running process. And of course, the properties should be at least the same or better than what's already achievable with long glass fiber pellets. And this is where our DirectPro injection molding approach comes in. I would like to introduce firstly the equipment to you and then go into the process principle. So first thing that we have is about the chopping behavior for the glass fibers. In this example, it's glass fibers, but this could also be implemented for carbon fibers, aramide fibers, or any natural fibers. So typically, when you chop them from strands, you have the different lengths. These are free flowing, but they're also sticking together. So there's like always you have a kind of bundle of these glass fibers. On the other hand, when you directly chop it from a roving, you can have at least lengths of about 60 millimeters with a better fineness and have various producers in handy. So how can we feed these fibers to our injection molding process? Well, you need at least a cutting system and ideally a feeding system for your injection molding machine. So this could be, for example, a principle that you can see here. So there's a running wheel and a cutting wheel on the top of a side feeder where the fibers comes in. These fiber strands will be cut by the cutting wheel and then got sucked into as a dry conveyance inside the side feeder. That side feeder you can see here is a double screw extruder, which will also suck in the fibers and convey them as a side feeder into our injection molding barrel. This one you can see here completely assembled on a 2-platen DP injection molding machine from Yizumi. So in the picture on the left side you can see firstly the bobbin creel where our glass fiber bobbins are stored, and a vacuum unit which is necessary to suck the fibers inside the side feeder. And then a little bit bigger on the right side you can see on top the side feeder, which is used to chop and cut our fibers and on the lower part the side feeder with the motor and the gearbox, which will suck in our fibers inside our injection molding system. And here you can see how this is working in total. You have see here the principle of our injection unit with a screw system. There's already material inside the screw, and the side feeder, which is assembled on 2/3 of the machine barrel to the injection unit. And the side feeder is already equipped with the glass fibers out of the bobbin. So how is this working? At first, our screw is not completely filled, so the polymer without any glass fibers, but already with the bonding agents in total, or compatibilizers, is fed to the screw and then got molten up in the first part. As you can see here on the screw you have a screw which consists of at least two different parts of screw. The first one is a standard three-zone screw where our unfilled material is fed, compressed and molten up. And beyond that there's a second part of the screw where the glass fibers are fed in. And here at that part where the side cutter sits, the side feeder, the fibers are already chopped. Now you can see how the melting and conveying of the unfilled material is going on until that part where this melt comes closer to the side feeder. And at that side feeder our chopped fibers are put inside the unfilled polymer, which is already molten up. It's got wetting and homogenized, and so due to the screw rotating and axial movement of the screw, our two components, the glass fiber and the polymer, are mixed together, and the glass fibers are distributed very well. After that, the axial movement is starting, and the injection takes place, and the material is brought inside our mold. Here you can see then the demolding with a little screenshot inside the part, and you see as a principle the distribution of the long glass fibers inside our part, inside our box. And that's it. So now we are going on with the properties of these parts. Firstly, we start with the fiber length distribution. Here you can see a typical dog bone, which is normally used for tensile testing. And we will make an overview about the fiber distribution for 3 different sections: near the sprue, in the middle of the part, and far from the sprue. And what you can already see here, so with a fiber analysis, there's the average fiber length for the different parts. One is length averaged, the other one is weight averaged. And you can see there are already glass fibers from 500 micrometer up to 2500 micrometer, and the distribution over the part is pretty homogeneous. Next one will be the tensile testings. So therefore we have a tensile test setup, and the dog bones are clamped inside the clamping jaws. And with the low cells we make the tensile test. This is where the parts are broken after the tensile testing. And you can see that there are still some fibers sticking out of these of the parts where the parts are broken. So these are the results from this part, and what you can see here is that we have a very homogeneous, breaking phenomenon, and we can establish, even with that part, with glass fibers of at least 40 up to 50 megapascal in tensile strength. The second mechanical test we are trying out is an impact test, where we make these notched Sharpie impact test bars, which are then hit by an impact hammer, where the overall impact strength is measured. And the same as before, the parts after the breaking, you can still see there's a little notch where the parts are still hold together, but there are also, you can see the fibers which are sticking out of the zone where the bars are broken. And what could also be seen that we can at least reach a very high impact strength of averaged at least 13 megapascal. Okay, then we come to the last parts, which are what are the current activities that we have with DirectPro and with our customers. So what you can see here is that we have these safety shoe caps, which is one of our customer is producing with our new machine. And the other one is another idea is a big fan blade, which could also be very interesting for us due to the higher stiffness and impact strength of our system. We are able to produce such big parts with a glass fiber content of 30%. So that was the presentation from my side. Thank you very much for your time and your patience. I hope you enjoyed the presentation, and I wish you all well and have a nice day. Bye bye.